Okay, so now we're going to finish up talking in Chapter 9 about tectonic movement. And I want you to really think about the idea of folding and faulting and the tectonic movements that are going along with both of those activities, and then warping as a piece of folding. First, think about the term stress. There's a great image I want you to know about stress and strain. But stress is the force that's acting upon a point. So we're talking about stress on landforms, on mountains, on areas. Tensional stress is pulling apart land. So that would be a divergent plate. Compression forces are squeezing, and this would be convergent plates, and shearing would be kind of the twisting or the snapping seen in transform plate movement. Stress causes strain. So strain is the way that the rock or the land surface responds, and it can respond in a couple ways. It can fold, or it can fault, which means breaking. And so depending on the speed of the stress, and the amount of stress and the type of rock or land that's being stressed will result in different strains. So we're going to look first at folded landscapes. Folded landscapes are a result of compression forces, so tectonic plates moving together, and often the rock will respond in first being folded, so that it's kind of like squeezing. I think there's a video in the reading list that shows kind of a carpet being pushed together. But you get these different layers of rock that respond by the compression of these two areas as they're moving toward each other. And so some fold down into a syncline, or they sink. Some fold up into an anticline or a ridge. And they may fold or deform to a certain point, and then they may actually crack or break and have a fault. So you could have both events happening. So here is an example of a, let me go back to the other slide. This is an example of a syncline. You can see where that layer of rock has been pushed down, but you can also see kind of an anticline on this side with a different layer of rock is pushed up. And then the fact that this isn't continuous shows probably some faulting along that area. Here is an area outside of Barstow, California, that has been severely deformed, and you can follow these stratigraphic layers as they kind of are moving up and down. So it's been a lot of compression, a lot of deformation. There are three main types of faults that I want you to be able to identify: a strike-slip fault, a normal fault, a reverse fault, and then a landform called a Horst and Graben, which is a result of divergent faulting. So we'll look at these a little more detail. A normal fault is the result of divergent plates. So the plates are moving apart, and one area may slide down. So this is called the fault scarp, and this part of as the plates are moving apart, this surface has dropped down or moved in position to the other. So in a normal fault, the fault scarp has an obtuse angle or a very wide angle, and you can see that in that area. And this is an example of a large fault scarp in eastern Oregon where this is a normal fault. This is the processes, divergent faults and normal faulting that's created what's called the Horst and Graben in eastern Oregon, or in the Great Basin or the Basin and Range, where the Horsts are the uplifted areas and the Grabens are the down-dropped fault. The Fort Rock Basin is in one of these areas that's kind of created internal lakes or basins. The African Rift Valley, that's the next slide. So the Great Basin of the United States is shown in red circled here as a huge landform, and so this is a divergent area, so the North American plate is moving in one direction, and then there's some tension pulling against that, creating cracks in the ground, and then larger landforms. You can see the Rift Valley is also a divergent plate area that's creating faulting. Reverse faults create a fault scarp with an obtuse angle. So this is the result of compressing, so that the landforms are being compressed together and one piece of land is moved up over the other, creates a bit of an overhang here. So you can see the normal fault is that stretching, moving apart. The reverse fault is compressional forces. And this is just a nice example of kind of compression here in San Fernando, California, as this piece of ground was moving toward each other. The Himalayan mountains are a result of compression faults. The third fault type is a result of shear stress, and this is seen in transform faults. So a great example is the San Andreas fault, and if you look at the Pacific plate, it's moving in this direction. This piece of the North America plate is moving in that direction, and these are slipping past each other. Now, while there is a bit of a mountain range, they don't have fault scarps like the normal fault or the reverse fault, and there's not as much vertical displacement. But you can see the rift here. You can also see the displacement of that rift on that edge as the plates have moved against each other. Oh, come on. I'm so sorry. This thing is just being goofy tonight. I didn't do that. I swear I didn't do that. Hold on, I'm pausing. Okay, in my defense, I'm traveling and I'm not using my computer, so this is a little crazy. Okay, so what's really nice is look at this crop row, and you can see the result of transform faulting where this normally or originally a straight crop row has been offset. You can also see this in the highway, so there's the offset, the result of that flow. The Loma Prieta earthquake, the last large one in California, ended up creating quite a few pretty anomalous landscapes, and we'll talk about those in just a minute. A couple terms you need to know about earthquakes is the epicenter and the focus. The focus is the point of break, so where that earthquake actually originated. The epicenter is the point on the Earth's surface directly above the epicenter. And so the farther the epicenter is from the focus, typically the less effects will happen from an earthquake. One of the things in the Loma Prieta that was so devastating was it created a liquefaction event. And a liquefaction event is a way that soil gets super saturated and acts almost as quicksand and can intensify ground shaking. So when that happens, when water gets pushed up into the sediment layer, it pushes apart the rock and the gravel and the sand, creating this quicksand. So here's an example of the road responding to liquefaction. I don't know that one. You can see a little bit of the sand moving up into the upper columns of water. This whole field was originally grass planted and sand moved up into the field. This was a grass marsh where mud pots moved up into the land as a result of liquefaction. And in Japan, this area from ground shaking, the buildings didn't fall over from ground shaking. The buildings fell over because their foundation turned to just goo, quicksand, and could not support them. So if you look at this map of liquefaction susceptibility, you can see that all along in the red area it's high, in the brown it's very high, and these are areas along the bay in California that have been filled with rock and gravel, so it was a way to reclaim land for building. But let's look at what's on that landscape. So the potential for major issues from liquefaction are very high. Then the other event associated with earthquakes are tsunami events, and Japan just experienced a pretty devastating tsunami. Indonesia, a few Christmases ago, also experienced a dramatic tsunami, and people call tsunamis, misname them, but really they're just a wave generated by volcanic eruptions or by landslides, displacement of water. And the interesting thing is, out in deep water, people don't even sometimes know that they're experiencing a tsunami. They call them tidal waves, but that's a misname, because out to sea, you're not going to notice the impact of that wave until it hits land, and we'll talk a little bit more about that when we get to ocean processes. But here is the results of a tsunami that was generated from an earthquake in Alaska, and this was, I think this image is from the wave damage in Japan. And also just some of the images from the information or from the earthquake in Alaska. And so along the Oregon coast, I think this is an international sign, but you see this a lot along the Oregon coast. They're usually in blue. And in Oregon, the common wisdom is, if you feel any ground shaking, you need to get to higher ground, because given that we're on a subduction trench, and if there is a ground shaking earthquake, it could be a lot like the earthquake in Indonesia, where people didn't have a lot of time or warning to get to higher ground. So this chapter pretty much ends a lot of the endogenic processes. We're going to move on to kind of what's happening on the surface of the earth in the next few chapters.